Hello, everybody. My name is Adirane, and I'm a junior at South Brunswick High School, uh, currently taking AP Physics C. And I would just like to thank you for coming to our first live session and trusting me to and my knowledge to help you all with preparing for the AP exams. I really hope this helps you, me, and all of us ace this unique situation. I know this is an unfamiliar time for all of us, including me, but I think that these live sessions will really help us be the most prepared for the AP exams, which are fast approaching. Okay, without further ado, let's begin our lesson. Today we will be looking at the electricity and magnetism portion of the exam, AP Physics C. And what we're going to be doing is we're going to be looking at a free response question, more specifically the 2000 free response question, the third one. And we're going to be solving it step by step like we did yesterday. And for any of those who have watched yesterday's session or have participated in yesterday's session, if you have any comments on yesterday's or today's session, just please feel free to leave a comment on how the sessions went, just in case you found that something could be improved upon. I really do want to make these sessions better each time, and we want to make this as accessible and as efficient as possible. Okay, then. What we're going to be doing, we're going to start right away. And as always, if you have any questions whatsoever, I will be working through each of the parts of the question. But there will be some questions. So if you have any questions whatsoever while I'm working, or any step that you feel confused about, I kindly suggest that you use the chat feature and type it in, and after each part, I will check the chat and answer any questions to the best of my ability. Okay, so without wasting any more time, by the way, does anyone have any suggestions on future topics? If anyone has any suggestions on future topics, please put it into the group chat option at the bottom of the screen. There should be a chat option. Any questions can go there, any suggestions, or if there's anything wrong at all, there's probably not going to be anything wrong, but just in case if I made a typo or a mistake, just let me know right there. And we're going to get started right away. Okay, so, okay, let's begin right away with the 2000 AP Physics C electricity and magnetism free response question. Okay, so let's read it out loud and let's see what the question is asking us. Okay, a capacitor consists of two conducting coaxial, so which means they have the same axis, coaxial cylindrical shells of radius A and B, respectively, in length L, which is much greater than B. That's what those two greater than signs next to each other mean, okay? It means L is a lot larger than B. So the space between the cylinders is filled with oil that has a dielectric constant of kappa, which means they put oil and it serves as a dielectric, which I will explain shortly. Initially, both cylinders are uncharged, but then a battery is used to charge the capacitor, leaving a charge positive Q on the inner cylinder and negative Q on the outer cylinder, as shown above. Let R be the radial distance from the axis of the capacitor. Okay, now they give us this diagram, and they're just two cylinders, they're concentric. Well, actually, the better term is coaxial, because then they have the same axis through their center, which means their centers of both sides coincide with each other. Okay? So they're coaxial, and let's look at part A. Using Gauss's law, determine the electric field midway along the length of the cylinder for the following values of R in terms of the given quantities and fundamental constants. Assume end effects are negligible. So we're only going to be looking inside, and it's going to be deep inside, like in the center right over here. So we can neglect the edge effects. Okay, so what is Gauss's law? First, let's write out the statement of Gauss's law. Gauss's law states that the total electric flux, which is this expression looks kind of intimidating, but what it essentially means is that the total electric flux, the flow of the electric field through a closed surface, that's why there's this little circle here, through a closed surface, is equal to the total charge enclosed by your surface over epsilon naught. Okay, so that is the basic formulation of Gauss's law. Okay, so how would we find the electric field in between A and B? Okay, so that's basically what part 1 of part A is asking. How do we find this electric field? Okay, now, in order to find this electric field, first we need a surface. Gauss's law works for any closed surface. That's what this statement means, for any closed surface. But if you pick the wrong surface that you're going to use as a Gaussian surface, and the surface doesn't have to be real, this surface is a completely imaginary mathematical surface. And what I'm going to try to do is imagine a surface that exploits the symmetry, the cylindrical symmetry of our shape, that allows the calculations to become a lot easier. So to say what I mean, I'm going to use a Gaussian surface of a cylinder. I'm going to use it of a cylinder. And this cylinder will look like this. Let's use a red. So this will be our Gaussian surface. Well, pay close attention that this surface is not actually real, but it is rather a mathematical surface that surrounds the cylinder with the positive charge. Okay, so this will be our Gaussian surface. Now, why did we pick this surface? Well, we picked a cylinder because the charge is arranged in a cylindrical shape. That means that the flux through each part of the cylinder, simplifies because the angle between the surface, the cylindrical surface, which is coaxial, so has the same axis as the middle cylinder, the electric field lines are perpendicular to our Gaussian surface. Okay? And why am I saying this? What does this actually mean? It means that this just simplifies to EA, because at this distance, you're assuming that your field is constant at this distance, and because we picked the right Gaussian surface, the cylinder, the angle between the electric field and the Gaussian surface is always at a right angle, meaning that the dot product over here simplifies to E times A. Okay, E times A. Now, this equals the charge enclosed over epsilon naught. Now, what is A? Well, we have to decide. We have to make another decision. What is our A? Well, is there any flux of the field going out through these two base faces? These two base faces have no flux going through them, so we're going to neglect that area. But this area we can't neglect because that is the part of the surface that the field is passing through outward. So we have to take into account the area of this section of the surface, the lateral area. And the lateral area of a cylinder is 2 pi times the radius, and the radius of our Gaussian cylinder is r times L. Okay, so that is our area. So what we have basically is 2 pi r L E, where E is our electric field, equals our enclosed charge, and our enclosed charge is only the positive charge. So that is Q over epsilon naught. Over epsilon naught. Now, if we want to solve for E, all we have to do is divide through by 2 pi RL. This essentially is an equation. So what we get is E equals Q over 2 pi epsilon naught RL. Now you might be thinking we're done. Okay, we found the electric field. However, we did forget one thing. And we forgot that there is a dielectric. What is a dielectric? A dielectric is any material that is an insulator. It is an insulating material put between two plates of a capacitor in order to reduce the voltage difference in between the two plates. Okay? A dielectric is basically an insulator. It's an insulating material. It does not conduct electricity. As such, the actual electric field will be less than the value we just calculated. And the dielectric constant that we're given, kappa, is defined such that the actual electric field is equal to the electric field without the dielectric divided by kappa. So if we were to treat this as the electric field without the dielectric, then we would get our actual answer. Q over 2 pi kappa epsilon naught RL. And that is our real answer. That is our real answer. So it turns out that once you get a hang of which Gaussian surface you should use, this does not become hard at all. Okay. Now, let's look at part 2 of part A. Okay? Let's look at part 2 of part A. Now, we're given that B is less than R, which is much less than L. So that is our range. So we're looking at the electric field directly outside this cylindrical capacitor. okay? Now, let's use Gauss's law again, okay? Let's use Gauss's law again. Now, the total electric flux through a closed surface, okay, that's what this expression means. The total electric flux through a closed surface is equal to the enclosed charge divided by epsilon naught, okay? Now, you might be thinking, what is the enclosed charge? How do we begin? What should our Gaussian surface be? Now, I can tell you that you already have your answer. And you might be thinking, wait a minute, how do we have an answer already? Now, if you read the problem, you saw that the battery is used to charge a capacitor, leaving a charge plus Q on the inner cylinder and minus Q on the outer cylinder. So in effect, if I were to draw a Gaussian surface here, I'm going to draw a blue Gaussian surface, and we use the same symmetry, the same cylinder that we used for part 1. Okay, let's just draw our surface. If we were to use the same cylinder argument, well then now we have to take into account both the positive charge of the inner cylinder and the negative charge of the outer cylinder. And because this is plus Q and minus Q as they gave us, the total enclosed charge is Q minus Q, Q minus Q over epsilon naught, and this is equal to 0. This is equal to 0. Now, what does this actually mean? Well, because this tells us that the electric flux is equal to 0, but because we picked a cylinder, so any electric field lines, if they existed, would be perpendicular to the surface of this Gaussian cylinder, then the angle would be 0 between the area, which is perpendicular to the surface, and the electric field. So obviously, this 0 cannot be caused by the angle, and we have a non-zero area, leading us to the assumption that for part 2, the electric field is 0. So for electric field is 0. Okay, so now I'm going to open up for any questions at all about part A. So both part 1 and part 2. We're going to be opening up for questions. Let's look. Do we have any questions in the chat? I'm going to wait for a minute. Just wait for any questions. All right. The key to this is realizing how to use Gauss's law and how to pick the correct surface so that the calculation becomes a whole lot easier. Now, seeing as there are no questions, let's move to part B. And this part B is also a two-parter, but because each of these 2 steps are important, I will stop after each mini part. Okay, let's look at part B. Determine the following in terms of given quantities and fundamental constants. So 1 tells us the potential difference across the capacitor. What is the potential difference? Okay, the potential difference is the difference in potential. Sounds a little obvious, but it is more the work done per charge by the electric field, okay, and is equal to this expression, okay? This integral expression is equal to the potential difference, okay? And if we use this integral expression, okay, if we use this integral expression, we can quite easily find our potential difference between the inner cylinder and the outer cylinder. Okay, now, when we're looking at the cylinder, okay, and this is A and this is B, okay, what we're trying to find is what is the potential between this part and this part? Well, we're going to be traveling outward from the point of highest potential, which is right here. And one thing I like to do to try and figure out what our limits, what our boundary conditions are, what the boundary conditions are, is the, what I like to do is figure out what the electric field goes from the point of highest potential to the point of lowest potential. Okay, high potential would be where the electric field originates. Lower potential will be in the direction in which the electric field points. So obviously, this outer cylinder will be at the low potential. Okay, so we have negative. So we're going to go from high potential, which is at A, even though it is the shorter distance, to B. Okay, and we're going to be traveling in the same direction as the electric field. So this dot product over here essentially becomes a multiplication. So we have this, and we have our whole expression, 2 pi kappa epsilon naught r L dr. That is the integral that we need to evaluate. Okay, now it does look a little intimidating. So what we're going to do is take all the constants out. So that is Q is constant, 2 pi, kappa is constant, epsilon naught is also constant, L is a constant. And what we're going to do is remove this negative sign by using a property of the integral, which is to flip the limits of integration. So now B will be our upper limit and A will be our lower limit, which now makes sense since B is our larger distance. Now, the integral of dr over r is equal to the natural log of r. So essentially, we have Q over 2 pi kappa epsilon naught L times the ln of r from B to A. Okay, so now this gets us 2 pi kappa epsilon naught L times ln B minus ln A, and we can simplify it. We can simplify it using a property of the natural logarithm. Okay, and we get our final answer. All of this times ln of B over A. Ln of B over A. Okay then. Now, let's look at part 2. What is the capacitance of the capacitor? What is the capacitance of the capacitor? Now, the capacitance of the capacitor is equal to the charge over the potential difference. It is defined as the ratio of the charge on the plate to the potential difference between the two plates. So in actuality, we have Q And it's a lot better if we multiply by the reciprocal of all of this. So we have 2 pi kappa epsilon naught L over Q times the Ln of B over A. This cancels, that cancels, and we get our capacitance in one simple operation. And this is our value. 2 pi kappa epsilon naught L over Ln of B over A. So now let's see if you have any questions. Let's see. Oh, we have a question. Can you tell me what Gauss's law is? I forgot to note it down. Sure thing. Gauss's law is a law that relates the electric flux through an arbitrary closed surface to the enclosed charge. Okay, so if I had a closed charge over here, okay, plus Q, okay, I'm just sort of explaining what Gauss's law is, and I have an arbitrary closed surface, and arbitrary means like any closed surface that you have, okay, then the electric flux, okay, what is flux? Flux is a quantity that measures how the electric field sort of flows through a surface. Sort of sounds like the word flow, okay? How the electric field passes through a surface, okay? So if like over here, the electric field goes straight out of the surface, all of it. So there's a relatively high amount of flux through this portion of the surface. And what if like over here, say over here, we have like this, it only like, it sort of angles like this. Okay, it sort of passes, not a lot of it passes through the surface, only like a little of it. That means there's not a whole lot of flux through that area, okay? So, what Gauss's law states is that throughout the entire surface, this total electric flux, which is given by this expression over here. And if you were to take like a multivariable calculus class, then you would know exactly mathematically this symbol means. But what it's saying is that the total electric flux through the surface is equal to the enclosed charge, which is in this case plus Q, over epsilon naught, which is a constant, but just a physical constant that does not change regardless of the situation. So effectively, it is dependent on the enclosed charge. I hope that answers your question. Okay, do we have any other questions? Thank you, may God bless you. May God bless you too. Okay, so let's look at part C. Okay, now this capacitor is discharged and the oil is drained from it. So apparently now there is no dielectric in there. There's no insulator. So it's just like a vacuum in between there. As shown above, a battery of EMF E, okay, is connected to the opposite ends of the inner cylinder, and a battery of EMF 3E is connected to opposite ends of the outer cylinder. Each cylinder has resistance R. Assume that the end effects and the contributions to the magnetic field from the wires are negligible. Using Amperes Law, determine the magnitude B of the magnetic field midway along the length of the cylinders due to the current in the cylinders for the following values of R. Now, when we usually do this, we assume positive current, conventional current in which the positive charge flows. Okay, that's just a convention we use. Okay, so in this case, the current will be from this battery will be flowing this way. So it will pass through the cylinder like this. That will be our current. Okay, that will be our current this way. Ooh, we're on. Okay, let's try to. Okay, so now we have a current going this way. The 3E battery also has the voltage source pointing the same direction. So what this basically means is that the current will be passing through this way. Okay, so what this means is that the current will basically be passing through this, passing through this way towards in the same direction. Okay, so now what does this mean? Okay, so what does this mean? Well, let's use Ampere's law. Ampere's law is another law. Okay, another law that relates, that's similar to Gauss's law. In Ampere's law, the statement is written like this. Okay, the total line closed line integral, okay, so the contributions of the electric field across a closed path, the sum of that equals mu naught, which is a constant, times the enclosed current. Okay, so what does that mean? Okay, what does that mean? If I have a current like this, that means if you were to use the right-hand rule, okay, you would point your thumb in the direction of the current and your fingers would curl in the direction of the magnetic field. So the magnetic field is constant right over here in a circle, okay? So that means if we choose a circular loop, a circular Amperian loop, that means the individual contributions of the magnetic field through each part of the loop will be the same. So essentially, you're basically summing up the length of the loop since the magnetic field is constant along the loop. So what I'm trying to say is if we use a circular loop as highlighted in green, then we get a nice simple expression because we only sum up the circumference of the loop, which is 2 pi RB. And what is the enclosed current? Well, in this case, you can use Ohm's law, which relates the current to the EMF and the resistance. And this current is caused by the EMF of E, that battery. So we have E over R. So essentially, we have 2 pi RB equals mu naught E over R. Okay, 2 pi R E B equals mu naught E over R. And we get, if we divide through by 2 pi R, we get our B equals 2 pi R, okay, below mu naught E. So mu naught E over 2 pi R, okay, capital R. So that is our magnetic field for A is less than R is less than B. Okay, now we can do a very similar thing. We can do a very similar thing for part 2. Okay, in this case, we make our statement of Ampere's law, which is this equals mu naught times the enclosed current. Now, there are two currents being enclosed. Sorry about that. That was a technical mishap. Okay, so let's, where were we? Okay, where were we? All right, so now we have the same concept as before, and instead of this orange current, which is the pink current, which is in the inner cylinder, we also have to account for this yellow current that is in the outer cylinder as well. The outer current, I out, is caused by 3E over R. So essentially, this becomes 2 pi RB, using the same reasoning as before, equals mu naught times E plus 3E, since the currents are facing in the same direction, over R. Okay, and if we divide, we get B equals 4 mu naught E over 2 pi R. And if we divide and simplify, we get 2 mu naught E over pi R, where B is less than R and is much less than L. Okay, so now I'm open up for any questions at all about what we just did. I'm going to check the group chat, and okay, we're gonna see if there are any questions on part C. Okay, I'm gonna wait for a couple of minutes. Okay, so Ampere's law is a lot like Gauss's law. They both relate fields, electric field and the magnetic field, and they both relate enclosed quantities. And for Gauss's law, it was enclosed charge. For Ampere's law, it was enclosed current. Okay, so if you know how to use one, chances are it's not super difficult to use the other. Okay, so I don't see any questions on the chat, so I'm assuming that all of you understand. Okay, it's not super difficult. It looks super difficult. It's not super difficult to see that if the currents are facing in the same direction, their magnetic fields will add up in the same direction as well. They won't cancel each other out. In fact, they'll add to each other. Okay, so that's it. We finished that question. So it looks very hard. It looks like we did a lot of calculation, but it's really, if you know what the formulas are, why the formulas are like that, and how to make your life easier by using the concepts of physics properly, then this stuff, all of this is not that difficult. And the sooner that you realize it's not super difficult, the much easier time that you will have on the exam. Okay, now, so, all right, so thank you. Thank you so much for coming to the session, and I am really glad that all of you were able to join the session, and I'm probably going to hold another session just like this tomorrow, okay, or most likely Monday at probably the same time. So please do leave feedback. Feel free to leave any feedback that you have on this session and suggestions on today's session. Like, did I explain well enough? Was that everything easy to understand? I want to make these sessions better. I can make these sessions better, but not without your suggestions. So please feel free to comment on how this session went. Okay, please leave comments on what I should cover next session. Okay, either like on my page where I will share the video shortly. And please do share my page with others so that a lot more people can benefit from these sessions. Okay, today was AP Physics C, Electricity, Magnetism. Okay, next session will probably be mechanics as well. Okay, I might review a concept, or I can do another question if if the question review is popular enough. Okay, looks like that's it. All right, thank you. Thank you so much for joining this session, and have a great weekend. Have a great Sunday. Okay, most likely our next session will be Monday. Thank you so much. See you next time, and goodbye.